My name is Karthik Ram Ramakrishnan. I'm a lecturer in Sustainable Polymers and Composites at the Bristol Composites Institute. Our CDT students come from a wide range of backgrounds, with degrees in mechanical engineering to chemistry. In the first year, they do a series of units. DBT is one of those units. The DBT stands for Design, Build and Test. But it's not just about the technical skills, it's also the soft skills that they learn. It's about time and project management. It's about learning to work together as a team, especially because research projects are never a straight line. You face a lot of challenges, you face many setbacks, and this unit is a kind of microcosm of the PhD research, where they face all the challenges and learn how to overcome them.
Yeah, so the DBT project at the start was presented to us as we have an idea for a sequential buckling, passively actuated wing spoiler. The task we were given was produce a demonstrator that can do that. Make a device that resembles a wing spoiler and use sequential buckling to make it work. So there are 10 of us. There are 10 of us in the cohort. 3 main groups. We had the modeling team, the manufacture team, and the testing team.
The main aims of the modeling were to model the post-buckling behavior of the beam and shell. At the start, we weren't lucky enough to use hand calculations for the initial design, so we had to go straight into using finite element analysis. We used the commonly used Abacus software. This is quite useful because it has a RIX step where you can do post-buckling analysis.
The tool that we use for layer up actually consists of 2 parts. The top part, which was aerofoil itself, which we use to wrap it, which mimic the shape we want to get, and a large metal plate, which we use to extend the front leading edge.
So for the laminates themselves, we use 2 different types of prepreg material. For the manufacturing of those, we were able to use an oven cure for one of them. We had to use an autoclave for another one. It was really good to have a comparison between 2 different materials, and that's really why we went with the 2 ones that we had. So again, from the modeling team, they explained to us it was very important the stiffness of the material that we used, and also characteristics like the thickness of the system as well. So having that stark contrast between a very thin prepreg material and a thicker, relatively thicker material.
Okay, this is the Shimatsu tabletop tester, and the main component is the crosshead, which during testing moves down into compression in the beam, which you can see here. And then we have the test strip itself, which is like an L-shaped bracket. So we have a bottom part, which is able to move around in order to adjust the position of everything, and the back bracket, which holds the tool and the composite plate itself into the correct place. The camera we are using is a photon high-speed camera, which is able to go from like 60 FPS to up to 1 million. And we chose a high-speed camera because we wanted to get the full motion during the contact between the plate and the machine. And so 60 FPS, which are the common frame rate for most cameras, we felt that it wasn't enough to capture the whole displacement.
The testing is going quite well. We've just finished this morning. We spent the last couple of days doing the actual testing itself, as the first week was spent just modifying the test rig as it wasn't performing the way we wanted it to. Yeah, the results we've seen so far have been pretty good. We've been conferring with the modeling team throughout the testing after each round to check that they're seeing similar results that we're seeing, and they are, so that's quite promising. We're quite glad that it's over and that it went well, but lots of the parts of testing is also the analysis of our results and going through those. So although the time in the lab may be done, there's lots of post-processing which we're going to have to do in the following week.